So, I welcome all you to the design of reinforced concrete structures for the week 4 session. Today, we will be discussing the design of doubly reinforced rectangular sections. So, you would have already gone through the lectures of week 3, in which you were taught limit state of collapse fracture. Lecture 7 lecture was design of doubly reinforced beam in fracture. So, I will be talking about that. So, firstly, I want to give you a brief theory about this, why we actually need doubly reinforced rectangular beam sections. Already you would have gone through the singly reinforced beam sections, so we are directly taking the doubly reinforced rectangular section because if we see in today's buildings everywhere, we don't require singly reinforced sections. Hardly we see anywhere singly reinforced section. Everywhere in our beam or framed structures we have doubly reinforced section. So there arises the question, why we why would we need doubly reinforced sections if we had already designed the singly reinforced sections? So we will see why we require these. So doubly reinforced sections we require when our dimensions are restricted. We require these sections when we have a restriction on the dimensions that we have to give to our rectangular section. These restrictions may be due to the aesthetics point of view, or in the design they said that you can't exceed for example say 1 meter depth of a beam, or you can't exceed zero point 0.5 meter width of the beam, because we only want you to occupy that volume or that space of our building. So you have to design within that specific section capacity. You have to design, as structural engineer is to be said that you have to design the section within those section parameters. So there comes the concept of doubly reinforced sections when we have restriction on the dimensions. Second point, we require these doubly reinforced sections in those positions when our singly reinforced sections become inadequate in carrying the moment capacity. For example, in our framed structure, we were having some singly reinforced beam. It was singly reinforced. For example, but now the loading case or loading scenario has changed to such an extent that the ultimate moment of resistance (MU) exceeded MU limiting on these. You would have already familiar with these terms. MU limiting. MU limiting is the moment of resistance of the section corresponding to the neutral axis depth to the XU limiting. So when the moment when the moments that are coming on this beam exceeds the limiting moment capacity of singly reinforced section, we have to shift to the doubly reinforced section. That is when MU is greater than MU limiting. Now, third scenario, we require these doubly reinforced sections at places when our structure is subjected to lateral loads. What I mean by that, for example, I have a building like this. It's a framed structure, single bay building. For example, earthquake load or wind load acts on this structure. What happens this by this lateral loads? Hogging moments get created in this beam. Here, hogging moments get created like this. It get hogged near to the joints here. For this, since we have, if we would have provided only singly reinforced section, our beam would have directly cracked due to this hogging moment. To prevent this, we provide the steel at the top of the beam as well. Here we provide as well, because we know at the top, mainly when it is subjected to only gravity loading, there is only compression at the top, which is resisted by concrete. We don't have any issue with that. Now when if it is subject to the reversal of the moments, like on the bottom side, and now the tension came at the top, Now we know that the concrete is very weak in tension. So as to avoid these situations, we provide reinforcement at top as well. Our main motive of this reinforcement is to provide the compression strength only, but in these scenarios, it also helps us to resist the tensile effects that are created by the hogging moments as well. These are the some of the applications. So directly coming to the design formulas that we will require. Sorry, nobody is saying that my screen is not visible. Should I at least? I'm sorry. Wait a second. Can anyone now confirm me is screen visible?
Yes, sir.
Okay. So I only gave the brief introduction about the design of this design of doubly reinforced rectangular section. I said that we require doubly reinforced section in the situation when our cross-section dimensions are restricted due to aesthetic points of view or any other space constraints or some other issues will be there. We require the doubly reinforced sections. Second point, I say said that when the loading on our structure increases to such an amount that the existing beams, which would have been singly reinforced sections, the moment on these beams have crossed the limiting moment resistance of that beam, so that they are no longer able to resist the applied moments. For those cases, we shift to the doubly reinforced sections. And third point, I said that when our structure is subjected to the lateral loads, I can give the example of the wind loads or the earthquake loads. What happens due to these lateral loads? This our frame structure gets subjected to the hogging moments. In beams, we primarily study there is only sagging due to the gravity loads which is downwards. Now, when these hogging moments also come into play, our concrete is very weak in tension, which would be subjected when the beam is subjected to hogging moment. Now, as to prevent it, we also provide the compression steel at the top, whose main primary objective is to add the compression strength to that section. But in addition to it, it also provides a tensile strength on that side as well when it is subject to the hogging moments. So now I directly come to the design formulas. Here in this section, you can see this beam section. It's a doubly reinforced section. It is provided with AST at the bottom and compression steel AST at the top. Now, what I can say, these are the strains in the fibers. At the top, ESC. We have written this ESC as because it is the strain in the compression steel, and we have written this AST. T subscript stands for tension steel. EST. Now, I can divide this doubly reinforced sections like this. For example, I have one section like this. I denote it by doubly reinforced. I can equivalently put it as like this. It is a concrete section, singly reinforced. I can say that it is a singly reinforced. Plus, I draw an imaginary section in which concrete is not playing any role. That's why I draw an imaginary section. Actually, it is not a concrete section. It only contains the compression steel that I have provided at the top. Now, for example, if we have, I have provided all the tension steel here in the singly reinforced section. Now this section becomes, uh, I think, inadequate, or it doesn't have any functionality. It will not carry load unless it creates a moment there. So for that, I have to provide tension moment as well, because I have to resist this compression with this tension as well. So from total AST that I have provided here in this, I give one sum of this AST here, A1, and some AST here, A2. What I said that AST I distributed it between two parts, A1 plus A2, and this is ASC already there. ASC. You can see here in this figure, AST, one AST is given this here, and another is delta AST. I will let you know what this is, and ASC is at the top. What I do, I take this singly reinforced section from this doubly reinforced section up to what limit? Such that its moment carrying capacity is up to mu limiting, such that it resists it resists the moments up to its limiting capacity, mu limiting, and then I get an additional benefit of moment from this ASC and A2 that I deducted from this doubly reinforced, such that singly reinforced section plus this steel section I get back doubly reinforced section. So the total, if it was having total moment resistant capacity mu bar, I bifurcated into two things: mu limiting to plus some additional moment benefits that I got from by adding the compression steel. This is the basic philosophy behind this of using doubly reinforced section. I used singly reinforced section up to limiting capacity and added compression steel to it so that I can get some additional limiting capacity, additional moment carrying capacity. Now, here you can see that it is a singly reinforced section. We can use our singly reinforced section philosophy that I already solved one problem in the week 3. 0.447 FCK is the stress block, and it is having a lever arm of D minus 0.416 XU. And we are using XU max because we have changed it to a limiting section or balanced section. And for this only steel section, that's why it's already shown in dotted line, because it's actually not a concrete section and reinforced concrete. It is only having compression steel, which is creating one force, compression force of FSC minus 0.447 FCK ASC, and down at the bottom is delta AST, which has been which is the AST minus AS limiting that I provided here. And here the lever arm will be D minus D dash. Now this D dash will be the effective depth from this side. This will be D dash, will be this D dash. So now how we will calculate the force carried by the this ASC? This will be simply like this. So we had concrete section like this. That hollow section is not full section, it's hollow section like this. It's only containing the steel. We have ASC steel here. So what will be the force carried by these compression steel bars? First we will have FSC, and we will have to take the strength of the concrete that will be replaced by these bars. As this lies in the uniform portion of 0.447 FCK, we will subtract 0.447 FCK concrete strength from this FSC, and we will multiply by ASC. For example, for our simplification purpose, we sometimes neglect this term also, 0.447 FCK, because if you do finally the calculation, this 0.447 FCK doesn't have that much effect. But for the exact solution, we just put it like that. And for the steel delta AST term, we already know it will be giving this compression force like this. This will be giving tension force like this. 0.87, it's already factored. 0.87 Fy delta AST. I already told you have to put a we won't put this compression steel at the top fiber. We will embed it at least some depth below the top fiber. Let it be D dash up to the centroid of the steel, and we had already effective depth up the centroid of the bottom steel. So what our lever arm becomes? It becomes D minus D dash, such that we will get that additional delta M moment capacity. Delta M moment capacity will be either this 0.87 Fy delta AST times lever arm. This is lever arm. I will write this as lever arm. So this is the basic thing behind it. First was mu. I split it into mu limiting plus delta mu. This was the first formula. Same, for example, if I give limiting moment of resistance, if this section is able to carry limiting moment here, So the corresponding steel provided to it will be also the PT limiting percentage of steel. So I can write total PT that I will be providing in the doubly reinforced section will be a summation of limiting steel percentage plus additional steel percentage as compression steel that I will provide PT. And AST I already told you I bifurcated that into AST limiting plus delta AST. Delta AST. Now from this uh, delta mu, if I take this equation first, delta mu mu is equal to 0.87 Fy AST into liver RM. I can write na delta AST from this like this, delta mu divided by 0.87 Fy into liver RM. I can write liver RM directly from D minus D dash here. Now see this delta mu here, which implies delta mu from this equation will be mu minus mu limiting. I can write the mu limiting directly as delta mu as mu minus mu limiting divided by 0.87 F by D minus D dash. So this is one of the formulas for calculating the additional steel that we need to provide for making it a doubly reinforced section. Similarly, I can do one thing to this. I can rearrange this as I have another term, dimensionless term, or is equal to mu by bd square. I divide mu by bd square, I get a dimensionless term r. Another r limiting will be then corresponding to mu limiting by bd square. bd square. So when I substitute mu as r bd square and mu limiting as r limiting bd square and rearrange the terms here, I get here and take bd here right hand side. I write this as ast divided by bd. bd is the cross section multiplied by I will give as this 100. If you see this will become pt percentage, and my right side will become r minus r limiting I have to give multiply 100 from this also, this side. R minus R limiting. BD we took common from this side, so I have to take BD from this also. This will become 0.87 Fy. I have to take D from this common, 1 minus D dash by D. D dash by 100. Now this becomes PT. Whole becomes P, delta PT, delta AP, delta PT. Delta PT, and if I put this 100 on this side, delta PT by 100 becomes R minus R limiting divided by 0.87 Fy 1 minus D dash by D. Actually, this formula is a design aid formula. For that you only require D dash by D ratio. You know a doubly reinforced section. If you have D dash by D ratio this, and correspondingly you will get delta PT as this. You can use these design handbooks also, but we will follow our problem from the basics. Another formula for the compression area of the compression steel ASC, we can write it as 0.87 Fy delta AST divided by FSC minus 0.447 FC. You can write this formula from this hollow section. I told you in a hollow section we provide we provide ASC, we provide delta AST. So the compression force that we get here and the tension force we get here. If I equate compression force to the tension force, I will get this formula. You would have studied in the lectures in detail. And similarly, I can rearrange the terms to get the percentage PSC as 0.87 Fy PT minus PT limiting, because this delta AST is AST minus AST limiting. So rearranging term, I can write PT minus PT limiting divided by FSC minus 0.447 FCK. You can see their detailed derivation in the videos as well. Yes, yes, yes. I'm telling you these formulas because we require them in design. So this is the basics of basic formulas that we require. So let's come to the problem that we have to solve. In today's problem, we will take a section. We will take a section of width 250 mm and its depth will be 400 mm. So you are asked to design a doubly reinforced beam, but you have they have put a constraint that you can't exceed these dimensions: 250 by width and 400 by depth, and you are giving the freedom that you can design it as doubly reinforced beam. So loads that will be acting on it, it is having self weight, and it is having also 30 kilonewton placed at mid span, and it's also subjected to UDL of subjected to a UDL of 50 seconds. It's subjected to a UDL of 5 kilonewton. 5 kilonewton per meter. One second, I will come back. It's also subject to a dead load of 5 kilonewton meter. So the grade of steel is given as Fe415, and the concrete that we have to use is we can choose. Let us choose F20. Okay. Yes. Fe415 for an FCK we will take 25 MPa. So we have to first, there are the steps. First step will be calculating the ultimate moment that will be coming on our beam. For example, Actually, this beam is given as this simply supported beam. It is subjected to its self weight SW, and it is subjected to a dead load of 5 kilonewton per meter, and it is subjected to a 30 kilonewton at mid span, and it's, sorry I forgot to use its effective span. L is 6 meter. It is just like this, 6 meter, like this. First, from structural analysis, we will calculate the ultimate moment that will be coming on our beam section, maximum moment, because we will be designing our section for the maximum effectors. Because if our section is safe for the maximum effectors, it will be obviously safe all the effectors which will be below it, all the moments which will be below it. So step 1 will be calculation of ultimate moment coming on our beam section, mu. So for first we will calculate the dead loads acting on our beam. Dead load will be first the 5 kilonewton per meter load acting on it plus W due to self weight. So first self weight will be equal to, we have 250, here we have 250 mm. It is equal to 0.25 meter multiplied by 25 kilonewton per meter cube, the density of this concrete, reinforced concrete section, multiplied by we have gross depth as 400. 400 mm is equal to 4.4 meter. So meter square meter cube goes, it comes out to be 2.5 kilonewton per meter. It's also, these all were dead loads. Live loads also acting on that. Live load of 10.0 kilonewton per meter. Also having a live load of 10 kilonewton per meter. Sulfate. So factored dead load will be equal to WU, whole live load plus dead load as well. 5 plus we had this 2.5 dead, 2.5 as sulfate plus 10 as live load times 1.5. 1.5 comes as the load factor. It is 1.5 times dead load plus live load. Okay, this is the worst combination that we have to chuck for our calculating the ultimate moments. It comes out to be 26.25 kilonewton per meter, and concentrated load is acting as 30 kilonewton, but we have to convert it as a factored load. So multiplying it also by 1.5 into 30, this comes out to be 45 kilonewton. We have to take care it's acting at the midspan. So we will calculate, we have already calculated the factor load, so we will calculate the factor moment then. MUS, look, this whole WU is acting as a uniformly distributed load. So effect from it as maximum will be WU L square by 8. Will be aware with this formula. And from this concentrated load, maximum moment will be coming at WU L by 4, and the section of, the location of this section will be at the midspan. Substituting all the values of capital W, L, and we get maximum factored moment as 185.6 kilonewton meter. Now we have to calculate step second. Calculate limiting moment of resistance of section, MU limiting. From the code we have the formula for MU limiting, because limiting moment of resistance is a function of grade of concrete and the cross-sectional dimensions. And you have to also check it for the grade of steel. For Fe415, you can find the corresponding limiting moment of resistance as 0.1389 FCK BD square. This is corresponding to Fe415 steel. For Fe500 and Fe250, these are different. So when we put the values of FCK as 25 and B as 250 and D as so first I forgot. Let's first assume here effective depth as 350 mm. We have assumed we have just arbitrarily cut 50 mm for the nominal cover. We have put this as 50 mm for time being. Later we will revise our calculations. For time being, we put 50 mm as nominal cover and set that our so that our effective depth comes out as 350. 350 plus 50 is equal to gross depth 400. So putting all the values 0.1389 FCK 25. Our B is 250 into D is 350. This will be this will come in Newton per mm. This comes as 16.3 10 power 6 Newton mm. Here it is actually 25 megapascal, that is Newton per mm square. These are mm square cancels, and this is mm cube whole. So square cancels, there remains Newton mm. So the converting factor is 10 power 6 Newton mm converts to 1 kilonewton meter. So this is 106.3 kilo Newton meter. Clearly, first you will get the one indication here, mu, that we already calculated the moment that will be coming on our beam, 185. The moment if it would have been singly reinforced section, it would have been able to resist only 106. So we have to go for a doubly reinforced section. Mu greater than mu limiting, which implies that doubly reinforced section needed. Okay. So third step. In third step, we will be determining the compression reinforcement that we have to put for making it doubly reinforced section. Calculate ASC. So first we will calculate for ASC. I already told you AST total is equal to AST limiting plus delta AST. We have to calculate delta AST. Then from that we will calculate ASC. So this is AST. We have to calculate AST first. Then we will calculate AST limiting and delta AST. We will get total AST that we have to provide it first in the balanced section, and delta AST to the that section containing the steel only. AST limiting we can get directly from the formula, because AST limiting is for the balanced section. AST limiting. For first we will calculate the percentage of the steel for it to be balanced. PT limiting, we have a formula, direct formula for this, 41.61 FCK by F5 XU max by D. XU max by D. These all we have FCK given, Fy given, XU max by D for Fe415 is also given. Fe415 XU max by D. So substituting all these values in this 41.61 FCK, we have to put this value. XU max by D for FE415. XU max by D for FE415. This is 0.4791. 4791. So point 47 FGK25. This is 415. Can Newton units cancel here? It's also dimensionless. It will be 0.4791. Calculating this, what we get 1.2% PT limiting. From this we can get AST limiting directly as AST limiting will be equal to 1.2 divided by 100 into B, it is 250, into D, it is 350, because our percentage is equal to PT is equal to AST BD into 100. From this formula we got this. So this will be equal to 1051 mm square. So this much amount of steel we have to put for limiting section only. So we will proceed like this. Now we are in further formulas we also need this. We also need this D distance, D dash distance. So for time being, I am assuming these bars ASC. ASC are of ASC I am assuming 20 mm diameter bars for compression steel. Okay. From this I will get D dash will I will calculate D dash. I will put clear cover as 30 mm plus it will be surrounded by stirrup like this. It will be surrounded by stirrup like this. Stirrup of 8 mm. I am assuming 8 mm stirrup. Stirrup plus half bar diameter will be their half, this 5 by 2. 5 by 2 will be equal to 10. So I will get D dash approximately as 30 plus 8. 38 plus 10 equals 48 mm. 48 mm. So delta AST I will be requiring. I have a formula for that as mu minus mu limiting. I already wrote it. Mu minus mu limiting 0.87 F5 D minus D dash. We have all the values with us. We have mu limiting as 186 in 10 power 6 Newton mm, because we have to put every unit in unit Newton mm, and mu limiting is 106 into 10 power 6 Newton mm. We have this 0.87 Fy is 415 Newton per mm square. Our D is 350 and D dash we assume 48 on our assumption already above mm. From this we get delta AST required as delta AST required 734 mm square. So our AST required will be already placed AST limiting that we calculated 1051. AST limiting 1051 plus delta AST 734 comes out to be 1785 mm square. Now you got this value 1785 mm square. So you have to arrange this 1785 mm square in the number of bars. So if I consider number of bars, let number of bars be 3, n equals 3. So we have to equate AST to n pi by 4 d square. So I have AST as 1785 mm square. I thought I assumed let I put 3 bars at 3 bars. Pi by 4.785 evaluates and d square. And I calculate d from it. D comes out to be 27.5 mm. Now as a designer you will not give in design I am putting 27.5 mm diameter bar because 27.5 mm diameter bar is not commercially available nor it's being manufactured. So you have to put number diameter report the diameter as the available diameter that is being manufactured. So I can provide 3 numbers of 28 mm. If I calculate how much it will be AST provided, it will come out to be from design charts. You can directly see that what is the cross sectional area of 128 mm bar, and we are providing 3 1 cross section 128 bar is 616 mm square, 616 mm square. It comes out to be 1848 mm square. This is the amount of reinforcement provided. I will underline this that I provided already. So I already assumed 50 mm. This full cover, nominal cover 50 mm. But now I got what I have to provide as 28 mm bars. These 28 mm bars. So my calculation gets revised because I have to calculate new D. D that I have to revise as now 400 was gross depth, and I'm providing clear cover everywhere as 30 top and 30 bottom as well. So I provided 30 clear cover plus 8 mm. I already assumed the stirrups. Now I provide the bar of 28 mm, that will be 28 by 2. So new D comes out to be 348 mm. I originally provided, which is less than 350 mm that I originally provided. So I have to revise my calculations by taking D as 348 mm. MU limiting will be same. In fact, our MU limiting will also change. It will not change that much, but it will change slightly. Let's calculate it once again. It will be 0.1389 FCK BD square. Now D square you have to put only 348 mm. When I substitute all the values as 0.1389 FCK is 25, B is 250, and now D is 348 square. This comes out to be 105 kilonewton meter. And AST limiting, again calculating the above values that were already calculated now with D as 348 mm. It will be 1.2 was percentage. We are multiplying by B as 250 and now D as 348. BD by 100 will be this. So AST limiting will come as 1045 mm square. So delta AST required now will be delta AST required will be MU. What is it is actually na MU minus MU limiting by 0.87 FY D minus D dash. Put new D here, that is 348, and MU Mu is already calculated as 186, but now we get Mu limiting new as 105 kilonewton meter. When we put all these values, we get 348 mm square. Earlier, earlier this value was 734 mm square required. So AST required will also change. We will check. So 1045 plus 748 will be equal to 1793 mm square. What we provided already. So we provided we provide this amount of steel, 1848 mm square. So actual AST delta AST that we provided, AST provided will be it will be 1848 minus a limiting this AST limiting 1045. It will be equal to 803 mm square. So we will now determine step, which will be step 4. Last, we determined AST, we determined delta AST also. Now only final calculation will be for ASC calculation. So for ASC we will see, first we will assume XU is equal to XU max. And what is our D dash by D ratio? It is 48 divided by 348. It is 0.138. So corresponding FSC we can check as, since we cannot use 0.87 Fi definition in the compression steel as well, because we have to use it for tension steel where the steel is fully yielded. Now for compression steel we have to use FSC. It's a table given in code. We have to use corresponding stress generated, compression stress generated in the compression steel for D by D ratio. When we interpolate this D by D ratio 0.138 for our FSC value, we get it as 344.7 megapascal. So we can calculate our ASC required as, for ASC we have the formula 0.87 Fy delta AST whole divided by FSC minus 0.447 FC2. When you plug in all the values of AST, FSC and FCK, we will get ASC is 869 mm square. So we got ASC is equal to 869 mm square, and equating again it as n pi by 4 d square is equal to 869 mm square. Let us choose n as 2. When we plug in this here, we will get d is equal to under root 869 divided by 0.785. 0.785 is actually pi by 4 into n is equal to 2. D will be equal to 23.5 mm. And if we choose n equals 3, putting n same here, we will get D as 19.2 mm. So I will go for 3 number of bars as compression steel. I will provide 3 numbers of 20 mm dia. what is comes out to be if I calculate ASC provided, it will be 3 into 420 mm dia, it is bar diameter AB is 340, that comes out to be 942 mm square. If you check, 942 is greater than the ASC required, this is required value. Okay, so we got all the values. Now let's tabulate the values what we got. We said that we have to provide ASC as 3 number 20 mm dia. We said that we have to provide AST as 3 number 28 mm dia, and we assumed stirrup 5 stirrup 8 and we calculated cover clear cover we assumed 30 mm, and for compression reinforcement we assumed D dash to be, we assumed that 48 everything. And one more thing what we assumed, so let's, these were the details that we for our section. Okay, so we can draw, give the final detailing of our section as like this. This is our section. We provided, I will write it by green, we provided the, we provided 3 at equidistance. Okay, we provided 3 at the bottom, and we provided 2 at the top, no, 3 also at the top, but these are smaller than the lower ones because they are only having a diameter of 20 mm, below are 28 mm. And I stirrup provided stirrup of 8 mm. Stirrup of 8 mm here, here, and we provided, and we can write all our details like this. Our section was given as 250 by 400, 400 mm, and we provided this as 3325, and this as 3285, and this is stirrup 85 8 mm diameter, and we provided D dash is equal to 48 and we provided here clear cover. Clear cover is from the outer side of the stair up to the outermost fiber as 30 mm. 30 mm. And later we can do other calculations as well. For example, we can do this calculation as well. If we put all the values, we can get this distance as well. Bar spacing as 53 mm, like this one. 30 mm. This is the beam section. This will be the final beam that we designed for our given loading. So this completes our session today. Thank you everyone for joining. Thank you.
Thank you, sir.